Okay, so welcome back. Let me say where we were last time. Okay, so we had seen the definition and some examples of vector spaces. Okay. The idea, kind of the main idea or reason that we were introducing this was we wanted to make an abstract definition. And I don't think I gave all the axioms, to be fair, but they were in the textbook. Okay, so we wanted to make an abstract definition which captured some of the properties of Euclidean space. Okay, so the properties of Rn. And then, of course, the goal, or some of the kind of the idea then would be, well, we kind of know some intuition about Rn, so we want to use our intuition of Rn, or more accurately, at least for me, I'm thinking about R2 or R3. Maybe someone can get intuition by thinking about four-dimensional Euclidean space. I certainly can't. Okay. To prove, to prove more general statements, or have further applications, more general applications. And we'll see that this is actually a pretty remarkably successful endeavor. Okay, so a lot of the intuition that you gain from working with the plane or R3 extends very easily to all vector spaces, or in some cases it's a little more work, but you still can gain a lot of insight into pretty general spaces. So let me just say something here. Since I want to say some of the properties of Rn. So note that at this point, we can't do geometry in Rn, or at least on a vector space. Okay, so the axioms of the vector space told you something about, say, you know how to add vectors, you know that you can multiply vectors by scalars. But if I want to know something like, well, let's see, if I'm in the plane, I might want to know something like the angle between two vectors. Or I might, even more basically know what the length of a vector is. Okay? So at this point, we can't do that. For general vector spaces, so you can think that right now we're kind of studying R2 or Rn, but without any geometric tools. This is kind of our starting point for the class. Okay? But instead of focusing on what we can't do, instead let's, see what we can do with a vector space. Okay? So what can we do? Well, we know if we have V and W, in V, then we can take their sum. We can add two vectors. And we also know that if we have V and V, alpha in F, remember this is so I'm using, this usually will mean R or C, but it can mean any field at this point. Then I can take alpha V. Okay, so I can multiply vectors by elements of the field. So therefore, kind of the general thing that I can do is I can take a collection of n vectors. I can take n scalars, so n elements of my field, and I can just form a linear combination. So this is definition, linear combination. I won't even write out anything, it's just you take alpha 1 V1 plus alpha 2 times V2 plus alpha n times Vn. Okay, so this is you can think it's, I'm just doing all that I possibly can, all right? I can take a bunch of vectors, I can add them together, and I can also multiply them by scalars. Okay, so I'm just going to write this for ease of notation. You just write sum from I equals 1 to n, alpha I v sub I. Okay? So let me give you one of the main definitions now, really, of the course. So a collection of vectors I'll say v1 up through vn is a basis for v if any any other vector v and v has a unique, and this is important, representation as a linear combination of the v sub i's. Okay, so as a linear combination v is alpha 1 v1 plus alpha n vn. Okay, so of course the vi, these are fixed, so these are the vectors that you're forced to use, and then the scalars can be just general elements of your field. Okay, so for some alpha I. Okay, so there's two statements here, right? The first is that you can write any vector as a linear combination of vectors in your basis, and the second one is that there's only one way to do it. Okay? Okay, so let me make just a remark, which does turn out to be an important remark, but not important immediately, or perhaps really for this class. So I'm assuming, or let me just say, there's also a notion of a basis for an infinite collection of vectors. Okay, so I could write, a script v is v1, v2, or it could be an uncountable, and it doesn't have to be a countable collection of vectors, it could be an uncountable collection, and it's just exactly the same property that any other vector in your vector space would be a linear combination of this now infinite set. Okay, so this is something which certainly comes up, but at least for now I'm just going to only assume that bases are finite. Okay, so let me give you some examples. Okay, so the first one is, well, for our favorite example of a vector space, so V is f to the n, so r to the n or c to the n. Then a standard basis is E1 is 1 in the first entry, zeros afterwards. E2 is a 1 in the second entry, all other terms 0, and En is zeros except for the last entry. Okay, so it's easy to see that for any vector in f to the n, I can write as a linear combination of such terms, or so when I write a vector in here, it's of the form, well, it looks like alpha 1, alpha 2, up through alpha n, and this is just alpha 1 E1 plus alpha 2 E2 up to alpha n En. Okay? So maybe I should say here, probably I could have put it up there, but the alpha i's are the coordinates, or this is just the definition or the terminology. So they're the coordinates of the vector v with respect to the basis vi. Okay, so this is of course inspired by the fact that we call these the coordinates of, say, a point in n-dimensional Euclidean space. Okay, of course you can have different bases, and in that case the same vector will have different coordinates with respect to the different bases. Okay, so as an easy example, maybe I'll just give another example. Well, 2, 0, 0, 0, all the way up to 0, 0, 2. So I'm just taking 2e1, 2e2, up to 2en. This is also a perfectly good basis for r to the n, or c to the n. And the coordinates in this new basis will just be half of whatever the coordinates were in your old basis. Okay, so the vector e1 with respect to this basis looks like a half of 2e1. Okay, so maybe I'll just give another example as an exercise, which is, to show that 1, 0, and 1, 1 form a basis for R2. Okay, and then, pick some random points in R2 and, see what they look like in this basis, right? What are their coordinates? Okay, so let me continue with the examples. Some from the vector spaces that we saw last time. So we saw polynomials of degree, say, less than or equal to n. This was a vector space, well, with coefficients in F, in our field F. We're an F vector space. So had this form. Again, there are lots of choice for bases. Kind of the standard basis is called the basis of monomials, which is just, well, it's the collection 1 t squared t to the n. Okay, so obviously any polynomial of degree less than or equal to n can, essentially by definition, can be written as a sum of terms in the field times these monomials. Okay, what's another example? Well, we saw there were Fibonacci sequences with real values. Okay, so remember, this was the vector space consisting of all Fibonacci sequences where the first two terms were arbitrary. So you had, alpha, they looked like alpha 1, alpha 2, and then alpha 1 plus alpha 2, alpha 2 plus alpha 1 plus alpha 2, etc. Okay? So here, and some of these I would like you to check for yourself, check the details. Here, a basis, again, there's plenty of choices, but one of them is just that you take the Fibonacci sequence 0, 1, 1, 2, 3, and so on, and the Fibonacci sequence 1, 0, 1, 1, 2, and so on. Okay? So you might think this is kind of surprising, in that you're looking at a set of sequences, right? So you'd think of this as a very large space, but yet there's a basis of just two vectors, right? Any Fibonacci sequence can be written as a linear combination of these two, okay? And of course, the point is that the Fibonacci, even though a Fibonacci sequence is an infinite sequence, it's completely determined by the first two numbers, real numbers that you choose. So it kind of makes sense that there's a basis consisting of two elements for them, right? There's kind of two free choices that you can make. Okay, so here's another example. So this example is supposed to indicate that a choice of basis, so maybe I'll put this here, the choice of the basis depends strongly on the choice of the field F. Okay, so what scalars you're allowed to multiply by certainly dictates what the bases are. Okay, so for example, R, the set R, as a rational vector space does not have a finite basis. Okay, so let me show that here. Well, if it did, then any real number, so R in the reals, would be a sum. You know, R is alpha 1 v1 plus alpha n vn. So for some, maybe I should say here, does not have a finite basis of any number of elements, okay, where the alpha i's are in the rationals. Okay. Now, since the rationals are countable, there's only countably many coordinates. So since the rationals are countable, there's a countable number of pairs, alpha 1 up through alpha n. Okay, so this is a finite Cartesian product of countable sets, so that's countable. Since it's a basis, the real numbers, okay, so these correspond bijectively to the real numbers, right, since it's a basis. Okay, so any pair, any collection of coordinates that I put in gives me a real number, and I can get all real numbers that way. That would imply that the real numbers are countable. Okay, so this is a contradiction, since the real numbers are uncountable. Okay, so you cannot have a basis. So of course notice the real numbers as an R vector space just have a one-dimensional vector, namely, 1 is a basis for R as a R vector space. Okay, so it just kind of unsurprisingly, I guess it, depends strongly on being, what field you're using. Okay, so let me give you another definition now. Similar. So we say V1 up through maybe Vm in V is a generating system. This is what the book uses. I think people also say spanning system. That's what I learned it as, but I'm going to stick with the book. If for any V and V, there's some linear combination which V is equal to. So V is equal to alpha 1 V1 plus alpha m Vm for some alpha I in our field. Okay, so notice it's exactly saying, i.e., it's a basis. The definition is same as the definition of a basis. but uniqueness is not required. Okay, so you can still kind of get to any vector. You can think of it as, you start with this set, and then you're allowed to add, you're allowed to multiply. It turns out you can get any single vector from this, okay? But in general, you might have many different ways to get to different vectors by adding and multiplying in different combinations. Okay, so for a basis, there's kind of a unique way to go. In general, if you just have a generating system, there's a lot of different ways to do it. Okay, so let me give you an example. So first, well, this is kind of obvious example. Any basis is a generating system. Okay, proof by definition. Here's another example. Well, you can start with a basis. And then add any collection of vectors. Okay, so just add in more vectors. Okay, so you can this will certainly be a generating system since the basis itself was a generating system. So you can take any, vector. It's going to be a linear combination of sums in your basis vector, so you'll certainly will be able to do it for this larger collection. But you'll have lost uniqueness, right? So any vector you add in could be expressed as itself or expressed as in terms of your basis. Okay, so we've lost uniqueness. So as an easy example, you can take R and the collection of vectors 1 and 2. Okay, so R is an R vector space. And then I can write, I could write 5 as 5 times 1, or it's 1 plus 2 times 2. Okay? So here, it's a little, obviously confusing because I'm not multiplying vectors. This I'm thinking of as vector. This is scalar. Okay? I'm not going to try to distinguish just for the real numbers, and generally you have to be careful about that. Okay, so let me give you another definition, which is kind of the other part of being a basis. Oops, that's not a plus. So a collection V1 up through Vn, and V is linearly independent, which I will probably shorten to something like this. Okay. If and only if I have a linear combination, so if I have alpha 1 V1 plus alpha 2 V2 plus alpha n Vn, and I got that this linear combination was somehow equal to the 0 vector. This is true. Well, there's kind of an obvious way to make this happen, which is just to have each alpha I be 0 in your field. Okay, and you're linearly independent if this is the only way to do it. Okay, so if alpha I is 0 for all I. Okay, so conversely, well, we say this collection is linearly dependent, which I'm sure will get shortened to lin-dip or something. If, 0 is equal to alpha 1 V1 up through alpha n Vn, and there exists an alpha I not equal to 0. Okay, so let me give a definition now, or sorry, a proposition. Okay. which is if you have a collection which is linearly independent, linearly dependent, okay, then we can write one of the terms, so there exists some collection, so there exists some v sub k, which is in this collection, equal to the sum of the other terms, to a linear combination of the other ones. So I not equal to k, I equals 1 to n, alpha I v sub I. Okay? So you're linearly dependent if and only if you can take one of the vectors and write it as a linear combination of other ones in the collection. Okay, so let's see the proof. I guess I'll go this way first. Okay, so if we have if linearly dependent, then there's a linear combination, so there's alpha 1 v1 plus alpha n vn equaling 0 for alpha I in F, and there's some alpha k which is not 0, right? We don't really know anything except that there's one term, right, which is not equal to 0, okay? Therefore, well, I can certainly pull that to the other side. So I get alpha k v sub k is minus all the rest of the terms. Let's see. I equals 1 to n. I is not equal to k. Alpha I v sub I. Okay? And now, since the alpha k is non-zero, I can divide, right? So I can, since this is non-zero, and I'm in a field, I can say v sub k is the negative, let's see, alpha I over alpha k to the n of the v sub i's, okay? Okay, so given, this linear combination which is equal to 0, we can find this one vector which is a linear combination of the others. Okay, and of course this will work for any v sub k where the corresponding scalar that's multiplied by it is non-zero. Okay, so those are the terms that we can write in terms of the others. Okay, so that's one direction. For the other direction, well, if you know that you can write v sub k, so v sub k is equal to the sum of the rest, maybe we'll use a different Greek letter, beta I v sub I, well then certainly we just write v sub k minus this sum to the n beta I is equal to 0, and this is a non-trivial linear combination. By non-trivial, I mean not all the terms are equal to 0, and therefore it's linearly dependent. Okay, so that's that proposition. So you're linearly dependent if and only if you can kind of solve for one of the terms in terms of one of the vectors in terms of the other vector, or collection of vectors. Okay, so now let's see. Okay, so I'm going to give this proposition, then maybe a corollary, and then be done for the day. So the proposition is that you're a basis, so V1, put this in, up through Vn, is a basis for V if and only if V1 up through Vn is, basis for big V is linearly independent and generating. Okay, so let me prove this. Okay, so the first direction, or if you have a basis, it's pretty easy to see that it has to be independent and generating. Okay, so how do you get this? Well, if you have a basis, so bases are generating, okay, just from definition. And I can write, so if I write alpha 1 v1 plus alpha n vn being 0, well, I know that there's one way to do this, right? I can just take 0 v1 up through 0 vn being 0. But since when I write a by the property of being basis, there's a unique representation. If I have another one, well, they have to be the same, so all the alpha i's are 0. Okay, so that gives linearly independent. So the fact that I can write 0 as kind of a trivial linear combination, and bases give me a unique way to do it, that's exactly the same as showing that they're linearly independent. All right, so let me give the other direction, which is a little more involved, but again, it's just going to be playing around with these sums. Okay, so what do we have to show? We have to show that there is, for any v in v, so for any vector in v, we have to find a linear combination of the v sub i's, where v is equal to this linear combination, and we have to show it's unique. Okay, so since v1 up through vn is a generating system, we know there exists some alpha 1 up through alpha n, so that v is equal to alpha 1 v1 up through alpha n vn. Okay, and now we have to show that it's unique. So suppose that there were two different ways to do it. So suppose there were two different linear combinations. So, i.e., v is equal to beta 1 v1 up through beta n vn. Well, then I can set v equal to both of these, so I can say that 0 has to be equal to alpha 1 minus beta 1 v1. So I should say, I guess, this is v minus v plus alpha 2 minus beta 2 v2 all the way up through alpha n minus beta n vn. Okay? And now by linearly independent, so by linearly independence, we must have that, since I'm writing 0 as these terms, we have that alpha I minus beta I is equal to 0 for all I. So therefore, the representations as linear combinations were actually the same. Okay, so alpha I equals beta I for all I. Okay, so that finishes that proof. So I'm just going to, finish with kind of a corollary of this characterization of a basis, and then call it a day. Okay, so kind of a corollary, not a immediate corollary, is that any finite generating system okay, for a vector space V, contains a basis. Okay, so in other words, if I have this collection of vectors, so v1, v2, up through vn is generating, then I can find some v sub I1 up through v sub ik, where the v sub I sub j's are elements here, so it's just a subcollection of these vectors where this is a basis. Okay, so you can think that, you know, a generating system is a basis, except you might have too many vectors, there's too many ways to represent elements in your vector space, but you can always cut them down and remove some vectors and get a unique way to write everything. Okay, so let me give you the proof. So first we know that v1 up through vn is generating. By the previous proposition, if v1 up through vn is linearly independent, we're done. So we have a basis. Okay? Otherwise, well, it's not. It's linearly independent. Oh, sorry, linearly dependent. Okay? By the proposition, I should know the word for not previous, but to back. Okay, so by the other, I'll say by the other proposition, this implies that there exists some v sub k in our collection, so that v sub k, so this kth vector, is some linear combination of the others, right? And now we claim that this is, if I remove the v sub k's, so, or sorry, just the v sub k, minus v sub k is generating. Okay, so why is this? Well, we know that we can write any vector v, so for all v and v, we get this linear combination. Plus alpha n v sub n. Okay. On the other hand, we've written the v sub k in terms of the other ones. So we get alpha 1 v sub 1 plus alpha k. And now it's a sum from j not equaling k, alpha j v sub j plus alpha n v sub n. Okay, so I've just rewritten v sub k as a sum of the others. Now, I don't want to go through and write down all of what this is to work out exactly what the coefficients are, but you certainly, once you multiply this all out, you'll get a linear combination of the v sub 1 up through v sub n, which misses v sub k, okay, since we've just written v sub k in terms of the others. Okay, so therefore, it is still generating. And if it's linearly independent, so if v1 up through v sub n minus v sub k is linearly independent, we are done. So otherwise, you know, rinse and repeat. Okay, so in other words, if it's linearly independent, we're done. If it is linearly dependent, you find another vector, right, as the sum of the others, remove it from the collection, and repeat. Okay, so maybe I'll leave this, you know, as an exercise. Fill in the details here. It's, I mean, I'll just say, writing it formally as an induction proof is a not bad. The argument is right there. Okay, so I will stop here, and thanks.